Okay, I'm going to add a few podcasts from this nice book by Christopher Karnauskas, who's a faculty at CU Boulder. Gives a slightly different perspective on ocean's role in climate, which is obviously very critical. We have addressed it in various ways without going into specific details, so I figured it's worth adding some of these details here. So he has a bunch of chapters, and I'm just going to extract few results from each chapter to add to what we have already learned in the introduction to climate and climate change. So let's start with the interface, ocean-atmosphere interface, and simpler ways to try to convince ourselves that the ocean and the atmosphere are strongly coupled, which already is fairly obvious when we looked at things like the El Nino and the various zonal modes of variability, for example. And here is another way to look at it. Maps of time average sea surface temperature here, and precipitation over the global ocean in these two plots here, and their corresponding correspondence colored by absolute value of latitude in the bottom panel here. Here the 27-degree sea isotherm and 5 millimeter per day are shown in solid and dashed contours respectively. So you can see here the relation between SSTs warmer than a certain threshold, which is typically referred to as the convective threshold. Numbers are somewhere around 27, 27.5 and so on and so forth. Nonetheless, you see that there is a strong correspondence in the low latitudes between warm sea surface temperatures and rainfall above 5 millimeter per day, which is a fairly significant amount of rain, especially if you add up the numbers for a year. Here you'll get more than 5 meters of rain. Of course, at high latitudes there are other processes, hydrodynamic instabilities and the rising air and storm tracks coming off of the continents and so on and so forth, instability of the jet stream, kind of the things we have talked about a little bit. But when you look at the distribution of rain again, you'll see there is high amounts of rain in warm waters with what we called as the ITCZ, the Intertropical Convergence Zone, with the SPCZ or the South Pacific Convergence Zone here. The Indian Ocean is a bit different because of the monsoonal circulation, and you can see there is cold temperatures or less rainfall around here off of East Africa, and again you see the storm tracks clearly producing rainfall. Southern Ocean is different because it's a channel and it has very different dynamics. Okay, and there are seasonal variabilities in these as well. So what can we do with this? We can also plot this with absolute latitude here with colder colors, so you plot it against sea surface temperatures and rainfall. So at high latitudes and cold temperatures, precipitation is pretty much close to zero, but as you warm up towards lower latitudes, so you can go to warmer colors here, precipitation begins to increase. But you can see that in the warm latitudes where temperatures are much warmer than at high latitudes, you still get very dry regions like the subtropical oceans where the Hadley cell is descending, so the rising air in the ITCZ is sinking, and that's where the deserts are getting formed on land as well. So even though temperatures are warm, you have precipitation that could be very low or reasonably high, depending on whether you are within the subtropical gyre or within the rain bands. And there is a strong nonlinearity as you approach the warmest of the temperatures. You can see that the precipitation increases very non-linearly, almost super exponentially, as temperatures cross this threshold that we talked about in terms of 27 degrees C convective threshold. Okay, so that tells you that there is definitely some strong relation between the ocean and the atmosphere. Of course, this doesn't tell you what selects the scales of, or the narrowness of this ITCZ, and what selects the scales of the evaporative bands here, and so on and so forth. Because looking at the 27 degree centigrade isotherm here, you can see that there are warm temperatures here, but the rainfalls are confined to a much narrower band. So the whole rising motion and sinking motion and their scales, they're not an easy problem to explain just by words, so we will leave it there. In terms of the quantities we typically look at, here are a graphic representation of some variable t that is a function of x, y, and z and time, so space and time. So if you look at temperature, let's say at a given x, y, and z in time, so you can see it's varying in time, and you pick a spot in time, let's say at t equal to 10, and plot it in x and y, and you will see that it may have a certain shape around it like this for a fixed time here. And you can take another spot here at a y and an x and look at the distribution in the z at this t, at this x, and this y, and you may get a profile like this, which we will come back to a little bit later on. Typically the low latitude temperature profiles would look like this, where you have vertically homogenized temperatures in what we will call the mixed layer. So we will do the mixed layer heat budget in this chapter. There is a sharp gradient we call the thermocline, which we have been introduced to already, and it merges with the deep ocean, which basically remains at fairly constant temperature. And we are only going down here to 500 units, which you can assume is meters. So obviously the deeper ocean that goes down to a couple of kilometers or more remains fairly constant, and this mixed layer itself can change in with season. So during the warm season the waters will be warm, mixed layer will be shallow, winds may be weaker, and during colder fall winter months the temperature may get colder, mixed layer may get deeper, the thermocline may get deeper as well. So you have seasonal variability of the mixed layer, seasonal variability of the thermocline in terms of the temperature gradient, as well as the depth of the gradient, because the mixed layer may get deeper, because the turbulent kinetic energy that creates this uniform homogenized density and temperature and salinity, with some complications in the vertical structure we'll come back to later, the seasonal dependence does determine how that varies, and of course there will be year-to-year variabilities as well. So just to add to that, these are the kind of typical processes that happen at various latitudes at the air-sea interface. We will not worry about biogeochemical fluxes like dimethyl sulfide and CO2 and so on, but if we look think about the heat fluxes, you'll have sensible heat flux, evaporation, precipitation. So evaporation, heating by the shortwave radiation. Ocean will emit long wave radiation. Some of the shortwave radiation will penetrate into the ocean. The bottom of the mixed layer here will be interacting with the deeper ocean with some shear at the mixed layer, because the wind forcing is going to be trapping momentum in the mixed layer. Of course there will be biology as well that we will not worry about. There could be sea ice formation in some places, which obviously releases brine or salt and can cause density increases and cause vertical mixing. And there are also the so-called Langmuir circulation that is related to how the wind circulation creates the horizontal cells in the horizontal vertical cells in the mixed layer itself, and there are internal waves that get radiated out and so on and so forth. So there are turbulent exchanges at the surface that we look at that will be critical for the mixed layer budget that we want to look at. So let me leave this introductory podcast here and come back and look at some of the equations which will help us understand the mixed layer heat budget of the ocean before we get set to look at how ocean plays a role in modulating the atmosphere and the climate, okay, at various time scales.